So, today I will be explaining the entire history of math. And it is quite a lot, to be honest. I did a lot of research, and this is also my first video. So, if you subscribed, it would be nice. So, get comfortable, relax, and enjoy. Picture this. It's around 35,000 years ago. You're in the Lubombo Mountains, which is in modern-day Swaziland. Someone takes a baboon bone and starts making notches on it. 29 notches to be exact. This thing, called the Lubombo bone, is probably the oldest piece of math we've ever found. Nobody knows exactly what they were counting. Maybe days, maybe livestock, maybe something else entirely. But the point is, they were counting. Humans had started keeping track of stuff. Now think about what that means for a second. Some person, tens of thousands of years ago, looked at the world and decided they needed a way to remember things. Maybe it was tracking menstrual cycles, which some researchers think based on the 29-day count. Maybe it was counting animals in a herd. Whatever it was, this person figured out that making marks on something durable could help them remember. That's abstraction right there. That's the beginning of representing quantities with symbols. There's another bone from around the same time period called the Ishango bone, found in Central Africa. This one has multiple rows of notches arranged in patterns. Some people think it shows early multiplication or even prime numbers, though that's debated. What's clear is that early humans were doing more than just simple counting. They were seeing patterns, relationships between numbers. For thousands of years after this, humans kept developing ways to track quantities. Some used knots in ropes, some used pebbles or shells, some carved marks into wood or bone. As humans settled down and started farming, the need for counting and calculation grew. You needed to keep track of harvests, measure land, count animals, plan for seasons. Fast forward to around 5,000 years ago, civilizations are popping up, people are building cities, trading goods, and organizing huge projects. And you know what you need for all that? Math. Lots of it. Now we need to talk about Mesopotamia first, because this is where things really take off. Around 3000 BC, the Sumerians in what's now Iraq developed something really clever. They created a number system based on 60. Yeah, 60. That's why we still have 60 seconds in a minute and 60 minutes in an hour. That's why a circle has 360 degrees. Think about that for a moment. A decision made over 5,000 years ago in ancient Mesopotamia still affects how you tell time and measure angles today. Why 60 though? 60 has a lot of divisors. It's divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That makes it really convenient for fractions and division. Some historians think it might have come from counting on fingers, using the 12 segments of 4 fingers on one hand, then using the 5 fingers of the other hand to count sets of 12, giving you 60. Others think it might relate to the approximate 360 days in a year. We don't know for sure. The Babylonians who came after the Sumerians took this even further. These folks were writing on clay tablets with wedge-shaped marks, which we call cuneiform. And on these tablets, they were solving some pretty advanced problems. They had multiplication tables, they could work out areas and volumes, they understood compound interest, they had tables of reciprocals to help with division. They could solve systems of linear equations. Here's something wild. On a tablet called Plimpton 322 from around 1800 BC, there are rows of numbers that appear to be Pythagorean triples. These are sets of 3 numbers where the square of one number plus the square of another equals the square of the third. This is 1,000 years before Pythagoras lived. The Babylonians knew about this relationship and were using it. They could solve quadratic equations, not just specific problems, but general methods. They had algorithms, step-by-step procedures for solving different types of problems. Some historians think they even tackled certain cubic equations. Their tablets show problems about finding dimensions of fields, calculating volumes of granaries, distributing shares of grain, and all sorts of practical stuff. The thing is, they approached math differently than the Greeks would later. For the Babylonians and Mesopotamians, math was practical. It was about getting stuff done, measuring land after the Euphrates or Tigris flooded, figuring out taxes, planning construction projects, keeping track of astronomical observations for their calendars and astrology. They didn't really care about proving why something worked. They'd have a method tested on specific cases. If you're building something, you need numbers that work, not abstract proofs. The Babylonians were also serious about astronomy. They kept detailed records of celestial events for centuries. They could predict lunar eclipses. They tracked the movements of planets. All of this required sophisticated arithmetic and developing tables of astronomical data. Their astronomical work would later influence Greek astronomy. Moving over to Egypt now, around the same time, people were doing their own mathematical thing. The Egyptians were masters of practical geometry. They had to be. How else do you think they built those massive pyramids? The Great Pyramid of Giza, built around 2500 BC, has a square base where each side is about 230 meters long, and the four sides are almost perfectly aligned with the cardinal directions. The precision is incredible. You don't get that without serious mathematical knowledge. The Rhine mathematical papyrus from around 1800 BC shows us what they were working with. This papyrus is like a textbook or reference manual. It contains 84 problems with solutions. The problems cover all sorts of practical situations. How to divide loaves of bread among workers. How to calculate the volume of a cylindrical granary. How to find the area of a triangle or a circle. How to work with fractions. They had a decimal system, which made sense because we have 10 fingers, but they did fractions in a weird way. They mostly used unit fractions, which are fractions with 1 as the numerator. So instead of writing 2/3, they might write 1/2 plus 1/6. They had special symbols for 1/2, 2/3, and 3/4, but everything else was built from unit fractions. This seems clunky to us, but they made it work. The Egyptians approximated pi. They figured it was about 3.16, which they got by saying the area of a circle equals the area of a square whose side is 8/9 of the circle's diameter. That's not bad. It's within 1% of the actual value. Close enough for building pyramids and temples, right? Their approach was all about trial and error. They'd work through problems step by step until they got an answer that seemed right. No proofs, no abstract theory, just practical solutions to real-world problems. They had formulas that worked, and they passed those formulas down. A scribe would learn the methods from their teacher, copy them down, practice them, and then teach them to the next generation. The Egyptians also used a base 10 number system, but it wasn't positional like ours. They had different symbols for 1, 10, 100, 1000, and so on. To write a number like 243, you'd draw 2 of the 100 symbols, 4 of the 10 symbols, and 3 of the 1 symbols. This works, but it makes arithmetic harder than it needs to be. Egyptian mathematics was tied closely to their bureaucracy and engineering projects. The pharaohs needed to know how much grain was stored in the kingdom's granaries. They needed to calculate how many workers and how much material a building project would require. They needed to survey land and reset property boundaries after the Nile's annual floods. Math was a tool of administration and construction. Now we get to ancient Greece, and this is where math totally changes. The Greeks, starting around the 6th century BC, did something nobody had really done before. They asked why. They wanted proofs. They wanted to understand the underlying principles, not just get the right answer. This philosophical approach to mathematics set them apart from everyone else. Thales of Miletus, who lived around 600 BC, is often called the first real mathematician. He wasn't content with knowing that certain geometric facts were true. He wanted to prove them logically. He proved that a circle is bisected by its diameter. He proved that the angles at the base of an isosceles triangle are equal. These might seem obvious, but he showed them using deductive reasoning. You start from basic assumptions, apply logical steps, and arrive at conclusions that must be true. This was revolutionary. Thales also used geometry for practical purposes. According to legend, he calculated the height of the Egyptian pyramids by measuring their shadows at the time of day when his own shadow equaled his height. He supposedly predicted a solar eclipse in 585 BC, though how accurately he could have done this is debated. But the key thing is his approach. He was looking for general principles, not just solutions to individual problems. Then comes Pythagoras, who you've definitely heard of because of that theorem. He lived around 570 BC, and he was kind of a wild character. He started a sort of secret society, the Pythagoreans, who had all these strange rules, and they thought that numbers were like the secret to the universe. The Pythagoreans made some legitimate mathematical discoveries. The Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. Again, the Babylonians knew about this relationship, but Pythagoras and his followers proved it, which made all the difference. They showed why it had to be true, not just that it was true. They also discovered something that totally freaked them out: irrational numbers. The story goes that they were looking at a square with sides of length 1. Using the Pythagorean theorem, the diagonal has to have length square root of 2. No matter how hard they tried, they couldn't write it as one whole number divided by another whole number. This violated their belief that everything could be expressed through ratios of whole numbers. Legend says they tried to keep this discovery secret, and when one of them, Hippasus, revealed it publicly, they either expelled him or maybe even killed him by drowning. That's probably just legend, but it shows how disturbing this discovery was to their worldview. The Pythagoreans studied music and found mathematical ratios there too. They discovered that pleasing musical intervals correspond to simple ratios. An octave is a 2-to-1 ratio. A perfect fifth is 3-to-2. A perfect fourth is 4-to-3. They saw mathematics everywhere, even in the harmony of music. Moving forward a bit, we have Plato, who wasn't primarily a mathematician, but had huge influence on mathematical thought. Plato believed that mathematical objects existed in some perfect realm of ideas, separate from the physical world. The circles and triangles we draw are just imperfect copies of the true, perfect circles and triangles that exist in this abstract realm. This philosophical view shaped how mathematicians thought about their work for centuries. They weren't just solving practical problems, they were discovering eternal truths. Plato's Academy in Athens became a center for mathematical learning. According to legend, the entrance had an inscription saying, "Let no one ignorant of geometry enter here." Plato emphasized the importance of mathematics for training the mind in logical thinking. Then we've got Euclid, who around 300 BC wrote The Elements. This book is insane. It's probably the most published math book in history, after maybe the Bible. It was the standard geometry textbook for over 2,000 years. Euclid took everything the Greeks knew about geometry and organized it into a logical system, starting from basic axioms. The whole thing is built on deductive reasoning. Euclid started with 5 postulates, statements assumed to be true without proof. Things like a straight line segment can be drawn joining any 2 points and all right angles are equal to each other. Then he built everything else from those postulates through pure logic. Theorem after theorem, each proved using earlier theorems and the postulates. By the end of the 13 books of the Elements, he'd covered plane geometry, solid geometry, number theory, and more. The 5th postulate, the parallel postulate, was always a bit controversial. It's more complicated than the others. It basically says that given a line and a point not on the line, there's exactly one line through the point parallel to the original line. For centuries, mathematicians tried to prove this from the other postulates, thinking it shouldn't need to be a separate assumption. They all failed, and much later, in the 19th century, mathematicians realized why. This postulate is actually independent. You can create consistent geometries where it's not true, but we'll get to that later. Euclid's Elements wasn't just about geometry. Books 7 through 9 deal with number theory, properties of integers. He proved there are infinitely many prime numbers. His proof is beautiful. Assume you have a finite list of all the primes. Multiply them all together and add 1. This new number isn't divisible by any of the primes on your list, so either it's prime itself or it's divisible by some other prime. Either way, your list wasn't complete. Therefore, there must be infinitely many primes. Archimedes, who lived from around 287 to 212 BC, was possibly the greatest mathematician of ancient times. This guy was brilliant. He invented methods for calculating areas and volumes that wouldn't be matched until calculus came along over 1800 years later. Archimedes figured out how to calculate the area under a parabola. He showed it's exactly 2/3 the area of the circumscribed rectangle. He did this by using a method of exhaustion, filling the space with triangles and showing that the sum converged to a specific value. This is basically early integration. He computed the volumes of spheres, cones, and cylinders. He showed that a sphere has 2/3 the volume of the cylinder that surrounds it, and this discovery meant so much to him that he wanted a sphere inscribed in a cylinder carved on his tombstone. Archimedes got a super accurate approximation of pi. He inscribed and circumscribed polygons around a circle, calculating their perimeters, and showed that pi had to be between 3 and 1/7 and 3 and 10/7. By using polygons with 96 sides, he narrowed it down pretty precisely. He worked on mechanics and physics too. He figured out principles of leverage and buoyancy. The story goes that he ran through the streets naked, shouting, "Eureka!" when he discovered how to measure the volume of irregular objects by water displacement. He supposedly said, "Give me a place to stand, and I shall move the earth about levers." The story goes that a Roman soldier killed him during the siege of Syracuse because Archimedes refused to leave his geometry problem. He was literally drawing in the sand when he died, supposedly telling the soldier, "Don't disturb my circles." Whether or not that's exactly how it happened, it's a perfect symbol of his dedication to mathematics. Greek mathematics also gave us people like Apollonius, who studied conic sections in incredible detail. He wrote a massive treatise on ellipses, parabolas, and hyperbolas, giving us much of the terminology we still use. Eratosthenes calculated the circumference of the earth by measuring shadows at noon in 2 different cities, Alexandria and Syene, and using geometry. His estimate was remarkably accurate. Diophantus, who lived maybe around 250 AD, worked on what we now call Diophantine equations, algebra problems looking for integer solutions. His book, Arithmetica, contained many problems and methods. He used symbols to represent unknowns, which was a step toward modern algebraic notation. Centuries later, Fermat was reading Diophantus when he wrote his famous note about Fermat's last theorem in the margin. The Greeks also had a mathematician named Hypatia, one of the earliest known women mathematicians, who taught and did research in Alexandria around 400 AD. She was a leading scholar of her time, working on geometry and astronomy. She was tragically murdered by a mob, which marked the beginning of the decline of Alexandria as a center of learning. But here's the thing about Greek math. It was mostly geometry-based. Everything was about shapes and lines and ratios. They had some algebra, like Diophantus, but they thought of algebraic problems geometrically. When they solved what we'd call a quadratic equation, they might phrase it as finding the side of a square with a given area. They didn't have the same kind of symbolic algebra we use today. They wrote everything out in words, which made complicated problems really hard to work with. And eventually, as the Roman Empire rose, the focus on pure mathematics kind of faded. The Romans were great engineers. They built amazing roads and aqueducts and buildings. They used existing math rather than developing new theories. Roman numerals worked fine for record keeping and basic arithmetic, but try doing complex calculations with them. It's a pain. The Romans inherited Greek knowledge but didn't push it forward much. There are exceptions, like Heron of Alexandria, who worked on geometry and developed formulas for areas and volumes. But the era of Greek mathematical innovation was ending. While all this was happening in the Mediterranean, China was developing its own mathematical tradition, and it was pretty advanced. Chinese mathematics goes back thousands of years. As early as the Shang dynasty, around 1500 BC, the Chinese had a sophisticated number system. They used counting rods, small bamboo or wooden sticks arranged in patterns to represent numbers and do calculations. This system was positional, with different positions representing different powers of 10, which was way ahead of what most other cultures were doing. By around 200 BC, they had the 9 chapters on the mathematical art, which is like their version of the elements. This book covered practical problems about agriculture, engineering, taxation, and trade. It had methods for solving linear equations, calculating areas and volumes, working with fractions, and dealing with right triangles. The problems were presented as practical situations with numerical examples, and then solutions were given algorithmically, step-by-step procedures to get the answer. The Chinese were using a decimal place value system over 1,000 years before Europe adopted it. This made arithmetic much easier. They also used negative numbers as early as the 1st century AD, representing them with counting rods of a different color. They understood negative numbers as debts or deficits, and they knew how to calculate with them. This was way before Europe would accept negative numbers as legitimate. They had methods for solving systems of linear equations using what we'd now call matrices. In the 9 chapters, there's a problem about buying different types of grain, and the solution uses a technique essentially identical to what we call Gaussian elimination today. But this was around the 1st or 2nd century BC, long before Gauss was born. The method is explained clearly, step by step. Around 1000 AD, a guy named Jia Xian came up with what we call Pascal's triangle. This triangular array of numbers, where each number is the sum of the two above it, has all sorts of interesting properties. The Chinese used it for calculating binomial coefficients, which come up in algebra when you expand expressions like x plus y raised to some power. Yang Hui and other mathematicians expanded on this, using it to solve various algebraic problems. Chinese mathematicians worked with magic squares, those grids where every row, column, and diagonal adds up to the same number. They saw these as having spiritual and philosophical significance. The oldest known magic square is from China, the Lo Shu square from ancient times, a 3x3 grid with numbers 1 through 9 arranged so everything sums to 15. The Chinese also made advances in algebra. They developed methods for finding roots of equations, including cubic and quartic equations. They used numerical approximation techniques. During the 13th century, which was kind of a golden age for Chinese math, mathematicians like Qin Jiushao, Li Zhi, Yang Hui, and Zhu Shijie were solving really complex polynomial equations. Qin Jiushao's mathematical treatise in 9 sections from 1247 includes a method similar to what we call Horner's method for solving polynomial equations. But again, this is centuries before Horner. Zhu Shijie wrote Jade Mirror of the Four Unknowns in 1303, which dealt with systems of polynomial equations and up to 4 variables. The techniques in this book were incredibly sophisticated. It was basically doing multivariate polynomial algebra at a level Europe wouldn't reach for centuries. The approach in China was different from Greece. Chinese mathematics was algorithmic and computational. They wanted methods that worked, step-by-step procedures you could follow to get an answer. They weren't as focused on geometric proofs like the Greeks were. The Chinese approach was more practical and calculation-based. They developed numerical methods, ways to approximate solutions. They used counting boards for calculations, arranging rods in patterns to represent numbers and manipulate them. Chinese mathematics was connected to astronomy and the calendar, which were important for agriculture and state purposes. The emperor needed an accurate calendar, and producing it was a major mathematical undertaking. Chinese astronomers made detailed observations and developed sophisticated models to predict eclipses and planetary positions. Now, let's talk about India, because Indian mathematicians made some contributions that literally changed the world. The big one? 0. Yeah, the number 0. This might seem simple, but it's one of the most important mathematical innovations ever. Now, no ponderance. The concept of 0 as a placeholder had been used before. The Babylonians had a symbol for an empty position in their number system. The Mayans in Mesoamerica independently developed 0, but treating 0 as an actual number in its own right, something you could calculate with, that's what the Indians did. Around the 5th century AD, a mathematician named Aryabhata, in his work Aryabhatiya, written in 499 AD, he described a decimal place value system and used 0, though he didn't have a specific symbol for it yet. He indicated it by absence. But it was Brahmagupta in the 7th century who really nailed it down. In his book Brahmasfuta Siddhanta, written in 628 AD, Brahmagupta treated 0 as an actual number with its own properties. He wrote rules for how to do arithmetic with 0. When you add 0 to a number, you get the number. When you subtract 0, same thing. When you multiply by 0, you get 0. When you subtract a number from itself, you get 0. This stuff seems obvious now, but back then, it was revolutionary. Brahmagupta even tried to define division by 0, though he got this part wrong. He said a number divided by 0 is a fraction, with 0 in the denominator, which we now know doesn't work. Later, Indian mathematicians like Bhaskara in the 12th century would grapple with this and get closer to understanding that division by 0 is undefined. Brahmagupta also worked with negative numbers extensively, which he called debts, while positive numbers were fortunes or property. He showed how to calculate with both positive and negative numbers. He gave rules for adding, subtracting, multiplying, and dividing positive and negative numbers. Negative times negative gives positive. Negative times positive gives negative. All the rules we learn today. He also gave us the quadratic formula. He showed how to solve equations of the form ax squared plus bx plus c equals 0. His solution method is essentially what we still use today. He worked on quadratic Diophantine equations too. Equations where you're looking for integer solutions. The Indians had a whole different way of representing numbers using words in Sanskrit verse, which is pretty cool when you think about it. They'd compose mathematical texts as poetry, using words to represent numbers based on associations. So the number 1 might be represented by words like moon or earth, because there's one moon or one earth. 2 might be eyes or wings, because those come in pairs. This mnemonic system helped with memorizing mathematical rules and calculations. Aryabhatta also worked on approximating pi, and he was really good at it. He calculated pi as approximately 3.1416, which is incredibly accurate for his time. He said the ratio of the circumference to diameter is 62,832 divided by 20,000, which gives that approximation. Aryabhatta calculated astronomical phenomena too. He believed the Earth rotates on its axis, which was a radical idea. Most people thought the sky rotated around a stationary Earth. He calculated the lengths of the year and the lunar month very precisely. He developed methods for solving indeterminate equations related to astronomical calculations. Indian mathematicians worked extensively on trigonometry. They developed the sine function, which they called ja. They created tables of sine values. Brahmagupta worked out interpolation formulas to find intermediate values in these tables. Later mathematicians developed the versine, cosine, and other trigonometric functions. Later, Indian mathematicians like Bhaskara II, who lived in the 12th century, continued this work. Bhaskara wrote several important texts, including the Lilavati, which covered arithmetic and geometry, and the Bijaganita on algebra. These books were written partly in verse, with problems posed as little stories or puzzles. Bhaskara had a daughter named Lilavati, and legend says he named his arithmetic book after her. Bhaskara worked on calculus-like concepts centuries before Newton and Leibniz. He understood ideas about instantaneous rates of change and calculated derivatives of sine and cosine. He worked with infinite series and found infinite series representations for trigonometric functions and pi. The Kerala school of mathematics in southern India, from the 14th to 16th centuries, took this even further. Mathematicians like Madhava discovered infinite series for pi, for sine, for cosine, for arctangent. They understood concepts of convergence and developed ways to improve the accuracy of their approximations. Some historians think these ideas might have influenced European mathematicians centuries later through trade routes and communication, though this is debated and hard to prove definitively. The Indian number system, the one with place value and 0 and 9 distinct symbols, plus 0, is what we use today. Well, technically, we call them Arabic numerals, but they came from India. So how did that happen? That brings us to the Islamic Golden Age, roughly from the 8th to the 13th centuries. During this time, the Islamic world became the center of scientific and mathematical learning. After the rapid expansion of Islam in the 7th and 8th centuries, the Abbasid Caliphate established Baghdad as its capital, and it became a hub of knowledge. Scholars in places like Baghdad, Cairo, Cordoba, and other cities were translating Greek, Indian, Sanskrit, Persian, and Chinese texts into Arabic. The House of Wisdom in Baghdad, established around 800 AD, was like a massive research institute and library. Scholars from different backgrounds and religions worked together, translating texts and building on them. They weren't just copying, though. They were improving, expanding, and making new discoveries. The star of the show here is Muhammad ibn Musa al-Khwarizmi, who lived from around 780 to 850 AD. This guy worked at the House of Wisdom in Baghdad. Al-Khwarizmi wrote a book called Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala, which means the compendious book on calculation by completion and balancing. That first part, al-Jabr, which means completion or restoration, is where we get the word algebra, and the word algorithm comes from the Latinized version of his name, algorithmi, two major mathematical terms from one person. Before al-Khwarizmi, algebraic problems were scattered around in different cultures with different methods. What he did was systematize it. He gave us general methods for solving linear and quadratic equations. He classified equations into 6 standard types. Things like squares equal roots, squares equal numbers, squares and roots equal numbers, and so on. For each type, he gave a clear procedure for solving it. Al-Khwarizmi showed how to do algebra for its own sake, not just for specific practical problems. He manipulated equations, moved terms from one side to the other, completed the square to solve quadratics. His methods became the foundation for algebra as we know it. He also wrote a book about the Hindu Arabic numerals and how to calculate with them, titled On the Calculation with Hindu Numerals. This book was eventually translated into Latin in the 12th century as Algoritmi de Numero Indorum, which introduced these numerals to Europe. The translation and spread of this book had enormous impact, gradually replacing the clunky Roman numeral system with the much more efficient decimal system. Al-Khwarizmi worked on astronomy and geography too. He made improvements to Ptolemy's world map and wrote astronomical tables. His work on the astrolabe helped with navigation and timekeeping. Other Islamic mathematicians were doing incredible work too. Omar Khayyam, who you might know as a poet, the Rubaiyat, was also a brilliant mathematician who lived from 1048 to 1131. He wrote a book on algebra, where he classified cubic equations and solved them using intersecting conic sections. He couldn't solve them algebraically, nobody would until later, but he found geometric solutions. He also worked on calendar reform and improved the accuracy of the Persian calendar. Al-Karaji, who lived around 1000 AD, extended algebra to include integer powers and roots. He worked with polynomials and developed methods similar to mathematical induction, though not quite in the modern form. He understood binomial expansions and worked on summing series of squares and cubes. Ibn al-Haytham, also known as Al-Hazan in the West, who lived from 965 to 1040, was computing sums of fourth powers and higher. He was working on problems that would later be solved using integration in calculus. He's more famous for his work in optics, writing a massive book that became incredibly influential in Europe. Nasir al-Din al-Tusi, who lived from 1201 to 1274, developed spherical trigonometry. He worked out the trigonometric relationships for triangles drawn on the surface of a sphere, which was crucial for astronomy and navigation. He also worked on Euclid's parallel postulate, trying to prove it from the other axioms, though he didn't succeed. But his work influenced later mathematicians who would eventually realize that alternatives to Euclidean geometry were possible. Ibn Sina, known as Avicenna in the West, was primarily a philosopher and physician, but he contributed to mathematics and logic as well. Thabit ibn Qurra worked on number theory and geometry, translating and commenting on Greek works while making his own contributions. The Islamic scholars preserved the Greek mathematical tradition when Europe wasn't really paying attention to it during the early medieval period. Greek works were translated into Arabic, studied and expanded upon. Without this preservation and development, much of Greek mathematics might have been lost. When these texts were later translated from Arabic into Latin, they kick-started the European Renaissance. Islamic mathematicians also developed early forms of mathematical proof. They worked on logic and philosophy of mathematics. They debated the nature of mathematical objects and the foundations of geometry. Their work on the parallel postulate, trying to prove it from Euclid's other axioms, laid the groundwork for the eventual discovery of non-Euclidean geometry centuries later. Europe during the Middle Ages wasn't exactly a hotbed of mathematical innovation, at least not at first. After the fall of the Western Roman Empire in 476 AD, learning declined in Western Europe. Latin was the language of scholarship, but fewer people could read it well. Most mathematical knowledge was restricted to monasteries where monks copied manuscripts. They preserved some mathematical works, particularly texts needed for calculating Easter and other liturgical dates, but there wasn't much original research happening. Things started changing around the 12th century when Arabic texts started being translated into Latin. Spain was particularly important for this. Parts of Spain had been under Islamic rule, and as Christian kingdoms reconquered these areas, they encountered libraries full of Arabic scientific and mathematical texts. Scholars realized these books contained knowledge far beyond what was available in Latin. Translation centers, particularly in Toledo, became crucial. Scholars like Gerard of Cremona translated dozens of works from Arabic to Latin, including Euclid's Elements, Ptolemy's Almagest, Al-Khwarizmi's Algebra Book, and many others. Through these translations, Europeans were rediscovering Greek mathematics and learning about the advances made by Islamic, Indian, and other mathematicians. One important figure was Fibonacci, whose real name was Leonardo of Pisa. He traveled around the Mediterranean with his merchant father and learned about the Hindu-Arabic number system. He saw how much better it was than Roman numerals for calculation. In 1202, he wrote a book called Liber Abaci, which means Book of Calculation. Despite the title, it wasn't about the abacus. It was about calculating with the Hindu-Arabic numerals. Liber Abaci introduced these numerals to Europe and showed how to use them for arithmetic, fractions, and solving problems. The book contained many practical problems about trade, currency conversion, profit calculations, and other business matters. It had word problems that required algebra to solve. Fibonacci showed how much easier calculations were with the new number system compared to Roman numerals. He's most famous now for the Fibonacci sequence, where each number is the sum of the previous two: 1, 1, 2, 3, 5, 8, 13, 21, and so on. This sequence appeared in Liber Abaci in a problem about rabbit reproduction, but his main contribution was really spreading the decimal system in Europe. It took a while. People were used to Roman numerals and resistant to change, but gradually the Hindu-Arabic numerals became standard. Universities were being established in Europe during the 12th and 13th centuries. Oxford, Cambridge, Paris, Bologna, and others became centers of learning. Mathematics was part of the curriculum, taught as part of the 7 liberal arts. The quadrivium consisted of arithmetic, geometry, music, and astronomy. Students studied Euclid's Elements, Ptolemy's Astronomy, and some Arabic texts in translation. The Renaissance in the 15th and 16th centuries brought renewed interest in classical learning and mathematics. There was a boom in art, science, and culture. Mathematicians were working on practical problems related to commerce, navigation, astronomy, and perspective in art. Artists like Leonardo da Vinci and Albrecht Dürer studied geometry to understand perspective and proportion. Mathematicians were particularly interested in solving polynomial equations. The quadratic formula was known, inherited from Islamic and ancient sources. But what about cubic equations? Equations involving x cubed and quartic equations with x to the fourth? Could these be solved by formulas? Italian mathematicians in the 16th century made breakthroughs here. Scipione del Ferro, around 1500, figured out how to solve certain types of cubic equations, specifically ones of the form x cubed plus mx equals n. He kept his method secret, as was common then. Mathematical discoveries were often kept as trade secrets, useful in mathematical competitions. Niccolò Tartaglia independently discovered a method for solving cubic equations. Tartaglia had a rough life. He was attacked as a child during the French sacking of his hometown, receiving severe wounds, including a cut to his jaw that left him with a speech impediment. His nickname Tartaglia actually means the stammerer. He taught himself mathematics and became quite skilled at it. In the 1530s, Tartaglia got into a public mathematical competition with another mathematician, Antonio Fiore. Tartaglia managed to figure out the solution just in time and won the competition. Enter Girolamo Cardano, a mathematician, physician, and notorious gambler. Cardano wanted to learn Tartaglia's method. He begged and pleaded and eventually convinced Tartaglia to tell him, making Tartaglia swear an oath not to publish it. But Cardano later learned that Del Ferro had discovered it first. Feeling the oath didn't apply since Tartaglia wasn't the original discoverer, Cardano published the method in his book, Ars Magna, in 1545. He credited both Del Ferro and Tartaglia, but Tartaglia was furious. Ars Magna also included solutions to quartic equations worked out by Cardano's student Ludovico Ferrari. So, by the mid-1500s, mathematicians could solve cubic and quartic equations by formula. Naturally, they tried to find a formula for quintic equations, equations with x to the fifth power. Generations of mathematicians tried and failed. It wasn't until the early 1800s that someone proved why they were failing. Turns out there is no general formula for solving quintic and higher degree equations using just arithmetic and roots. We'll get to that story when we talk about Galois. But the point is, Renaissance mathematicians were pushing algebra forward, finding general methods for solving equations. Moving into the 17th century now, and math explodes. This is when modern mathematics really begins. The 17th century saw the development of analytic geometry, probability theory, and most importantly, calculus. First, we need to talk about René Descartes. He lived from 1596 to 1650, and was both a philosopher and mathematician. You know the phrase, "I think, therefore I am"? That's Descartes. In 1637, he published a book on scientific method that included 3 appendices, one of which was La Géométrie. In this work, he developed analytic geometry. The key insight was connecting algebra with geometry. Descartes showed how you could represent geometric shapes using equations and coordinates. Every point in the plane gets 2 numbers, its x and y coordinates. A line becomes a linear equation. A circle becomes an equation, like x squared plus y squared equals r squared. Suddenly, you could study geometry using algebraic methods. You could solve geometric problems by manipulating equations. The Cartesian coordinate system is named after him, though actually it was developed gradually and Fermat had similar ideas around the same time. But Descartes gets the credit because his presentation was more influential. This merger of algebra and geometry was massively important. It meant geometric problems could be approached algebraically, and algebraic equations could be visualized geometrically. It opened up whole new ways of thinking about mathematics. Pierre de Fermat was working on similar ideas independently. Fermat lived from 1601 or 1607 to 1665. Exact birth date uncertain. He was a lawyer by profession, but did mathematics as a hobby. Fermat was also doing early work on what would become calculus, looking at tangent lines and areas under curves. He had methods for finding maxima and minima of functions, which is a calculus problem. He worked on what we'd call differentiation. His methods were clunky compared to what Newton and Leibniz would develop, but he was heading in the right direction. Fermat is most famous for Fermat's last theorem, though it wasn't actually a theorem, since he never proved it. He was reading Diophantus's Arithmetica and came across Pythagorean triples. Solutions to x squared plus y squared equals z squared. In the margin of his copy, Fermat wrote that there are no 3 positive integers, a, b, and c, that satisfy a to the n plus b to the n equals c to the n for any integer value of n greater than 2. He added, "I have discovered a truly marvelous proof of this, which this margin is too narrow to contain." For over 350 years, mathematicians tried to prove this, It became one of the most famous unsolved problems in mathematics. It was finally proved in 1994 by Andrew Wiles, using incredibly advanced techniques from modern algebraic geometry that didn't exist in Fermat's time. Most mathematicians think Fermat probably didn't have a valid proof. He likely thought he did but made an error, or had proved a special case and mistakenly thought his method was general. Either way, his marginal note inspired centuries of mathematical research. Fermat also worked in number theory, which is the study of properties of integers. He discovered what's called Fermat's little theorem, which says that if p is a prime number and a is any integer not divisible by p, then a raised to the power of p minus 1 is divisible by p. This theorem is used in modern cryptography. Now let's talk about the development of probability theory. Gambling problems led to some serious mathematics. In 1654, a gambler named Antoine Gombeau, the Chevalier de Marais, posed some questions to Blaise Pascal about games of chance. One question was the problem of points. If a game is interrupted, how should the stakes be divided based on each player's probability of winning? Pascal started corresponding with Fermat about these problems, and together they developed the foundations of probability theory. They figured out how to calculate probabilities for different outcomes, how to handle combinations and permutations. Pascal developed what we now call Pascal's triangle, though as we mentioned earlier, Chinese mathematicians had discovered it centuries before. Pascal used it to calculate binomial coefficients, which appear in probability problems. Pascal also wrote about expected value, the idea that you should weigh outcomes by their probability to make decisions. Pascal's wager, his argument about believing in God, uses this kind of probabilistic reasoning. Even if the probability of God existing is low, the potential infinite payoff of salvation makes belief the rational choice. Whether you find that argument convincing or not, it shows how probability theory was being applied to all kinds of questions. Christian Huygens, a Dutch mathematician and scientist, wrote the first published book on probability in 1657. He worked on expected values and probability in games of chance. This mathematical approach to uncertainty would grow into a major field with applications in insurance, gambling, science, and decision-making. But the really big story of the 17th century is calculus, and the stars are Isaac Newton and Gottfried Wilhelm Leibniz. Both of them independently invented calculus in the late 1600s. This caused one of the most bitter disputes in the history of mathematics. Isaac Newton lived from 1642 to 1727. He was born the same year Galileo died, which is kind of poetic. Newton was studying at Cambridge when the plague hit England in 1665. The university closed and Newton went back to his family's farm. During this period, which lasted about 18 months, Newton had his most productive time. It's sometimes called his annus mirabilis, wonderful year, though it was actually more than a year. During this time, Newton started working on what he called the method of fluxions. He was interested in motion and change. How do you describe the speed of something at an exact instant? How do you find the tangent to a curve at a point? How do you find the area under a curve? A fluxion, in Newton's terminology, was the rate of change of a quantity. If you have a function describing position over time, the fluxion is the velocity. The fluxion of the fluxion is acceleration. Newton developed rules for calculating fluxions, which is what we call differentiation. He also worked on the inverse problem. Given the rate of change, find the original quantity. This is what we call integration or anti-differentiation. Newton showed that differentiation and integration are inverse operations. This is the fundamental theorem of calculus, though Newton didn't call it that. It connects two seemingly different operations and makes calculus much more powerful. Newton used his calculus methods to work on physics problems. He was developing his theory of gravity and laws of motion. He showed that the force of gravity decreases with the square of the distance, and he could explain planetary motion using his calculus and laws. This all culminated in his masterwork, Philosophiae Naturalis Principia Mathematica, or the Principia, published in 1687. The Principia is one of the most important scientific books ever written. Newton presented his three laws of motion and his law of universal gravitation. He showed that the same force that makes an apple fall also keeps the moon orbiting Earth and the planets orbiting the Sunday. He could calculate planetary orbits. He explained tides. He showed that the Earth bulges at the equator. The whole framework of classical mechanics is laid out in this book. Interestingly, Newton mostly used geometric arguments in the Principia, not his fluxions. He may have used calculus to discover his results, but presented them geometrically, because that's what mathematicians of his time expected. Or maybe he wanted to make his work more accessible. Whatever the reason, his calculus methods weren't published in detail until later. Meanwhile, Gottfried Wilhelm Leibniz, living from 1646 to 1716 in Germany, was independently developing calculus. Leibniz approached it from a more abstract mathematical angle. He was thinking about infinitesimal quantities, infinitely small differences. He worked on sums of infinitesimally thin rectangles to find areas, which is the basis of integration. Leibniz developed really good notation. He introduced a differential notation dx and dy for infinitesimal changes. He used dy over dx to represent the derivative. He introduced the integral sign, that elongated s, which stands for summa, sum. His notation was intuitive and made calculations easier. It emphasized the relationships between quantities. Modern calculus uses Leibniz's notation because it's so much better than Newton's. Leibniz published his work on calculus first, starting in 1684 with articles in the journal Acta Eruditorum. Newton had been working on calculus earlier, since the 1660s, but he didn't publish it systematically until later. This led to a huge priority dispute. Who invented calculus first? Newton's supporters in England claimed Leibniz had stolen Newton's ideas. Leibniz's supporters on the continent said Leibniz was the true inventor and Newton was trying to steal credit. It got really nasty. The Royal Society in London investigated and, not surprisingly since Newton was president of the Royal Society, concluded that Newton was first and Leibniz had plagiarized. This was unfair to Leibniz. He definitely invented calculus independently. He came to similar conclusions through his own work. The truth is, they both invented it. Newton started earlier, but Leibniz published first and had better notation. Today we credit both of them. We call it the Newton-Leibniz calculus. But the dispute had lasting effects. British mathematics became isolated for a while, sticking with Newton's inferior notation, while continental Europe used Leibniz's notation and methods and made faster progress. Calculus was revolutionary. It let mathematicians deal with change and motion in precise ways. You could calculate instantaneous rates of change, velocities, and accelerations. You could find areas and volumes of complex shapes by integration. You could solve differential equations that describe natural phenomena, like the motion of planets, the vibration of strings, the flow of heat. Physics, engineering, economics, and so many other fields became possible in their modern forms because of calculus. It's hard to overstate how important this was. The 18th century saw mathematicians refining calculus and applying it to everything. But there were foundational issues. What exactly were these infinitesimally small quantities that calculus used? They were treated as non-zero when you wanted to divide by them. Mathematicians knew the results were correct, the methods worked, but the logical foundations were shaky. George Berkeley, a philosopher and bishop, wrote a criticism called The Analyst in 1734, calling infinitesimals ghosts of departed quantities. Though he was mostly trying to undermine the prestige of mathematicians to defend religion. Despite these foundational issues, calculus was incredibly successful. Leonhard Euler, who lived from 1707 to 1783, was probably the most productive mathematician ever. He wrote over 800 papers and books. He made huge contributions to pretty much every area of mathematics. In calculus and analysis, he developed the calculus of variations, methods for finding functions that minimize or maximize some quantity. In number theory, he worked on prime numbers, solved many of Fermat's conjectures, and discovered connections between number theory and analysis. In graph theory, he solved the famous Königsberg bridge problem, founding the field of topology in the process. In geometry, he worked on polyhedra and proved Euler's formula for polyhedra. V minus E plus F equals 2, where V is vertices, E is edges, and F is faces. Euler introduced so much notation that we still use today. The number E for the base of natural logarithms is named after him, though he wasn't the first to study it. He used I for the square root of -1, establishing complex numbers as legitimate mathematical objects. He popularized the notation f of x for functions. He introduced the capital sigma for summation and the capital pi for products. He established conventions for trigonometric functions. Euler proved what's often called the most beautiful equation in mathematics, e to the power of I times pi plus 1 equals 0. This connects 5 of the most important numbers in mathematics. 0, the additive identity. 1, the multiplicative identity. Pi, the ratio of a circle's circumference to diameter. E, the base of natural logarithms and growth. And I, the imaginary unit, the square root of -1, all in one simple equation. He worked on differential equations. He worked on partial differential equations, where you have functions of multiple variables and take partial derivatives. These are crucial for physics, describing wave motion, heat flow, fluid dynamics, and more. The Bernoulli family, particularly Jacob Bernoulli and Johann Bernoulli, made major contributions to calculus and probability. Jacob worked on the calculus of variations and discovered important results in probability theory. Johann tutored Euler and made contributions to optics and fluid dynamics. There was also a lot of rivalry in the Bernoulli family, various members competing and feuding with each other. Joseph Louis Lagrange, who lived from 1736 to 1813, worked on mechanics and the calculus of variations. His book, Mécanique analytique, applied calculus to mechanics systematically. He developed what's called the Lagrangian formulation of mechanics, which reformulates Newton's laws using energy concepts. This turned out to be incredibly useful in physics, especially for more complex systems. Lagrange also tried to make calculus more rigorous, defining derivatives using algebra rather than geometry or infinitesimals, though his approach had issues. Pierre-Simon Laplace, 1749 to 1827, applied calculus to celestial mechanics and probability theory. His Traité de mécanique céleste was a massive work analyzing the motion of planets and moons, explaining stability of the solar system. In probability, he developed Laplace transforms and the central limit theorem, which explains why so many things follow normal distributions. Laplace basically said that given enough information, the entire future could be calculated. He believed the universe was a giant clockwork mechanism running according to mathematical laws. Carl Friedrich Gauss deserves his own section because he was one of the greatest mathematicians of all time. As a child prodigy, he discovered mathematical patterns. The famous story is that when his school teacher tried to keep the class busy by making them sum all numbers from 1 to 100, young Gauss immediately saw the trick. Pair 1 with 100 to get 101, pair 2 with 99 to get 101, and so on. 50 such pairs gives 50 times 101, which equals 5050. Whether this story is exactly true or not, Gauss definitely showed early mathematical brilliance. Gauss worked in number theory extensively. At age 21, he proved the fundamental theorem of arithmetic, that every integer greater than 1 is either prime or can be expressed as a unique product of primes. This seems obvious, but needs proof. He studied quadratic reciprocity, a deep result about which primes can be expressed in certain forms. Gauss worked on complex numbers and proved the fundamental theorem of algebra, that every polynomial equation has at least one complex root. This means, if you include complex numbers, polynomials always have solutions. He showed that complex numbers are necessary and sufficient for solving polynomial equations. He made contributions to differential geometry, studying curves and surfaces. His work on the geometry of surfaces, particularly his theorema egregium, showed that the Gaussian curvature of a surface is an intrinsic property, doesn't depend on how the surface sits in three-dimensional space. This would become important for understanding general relativity. Gauss also worked in astronomy, physics, and geodesy. He calculated the orbit of the asteroid Ceres from limited observations. He invented the heliotrope for surveying. He worked on magnetism and electricity with Wilhelm Weber. The unit of magnetic field, the Gauss, is named after him, as are too many theorems and concepts to list. Gauss was careful and precise. He often wouldn't publish things until he'd worked them out completely to his satisfaction. His motto was few but ripe. After his death, mathematicians found many results in his private papers that he'd discovered years before others published them. He'd worked on non-Euclidean geometry but never published it, possibly because he thought it would be too controversial. Speaking of non-Euclidean geometry, this emerged in the early 1800s and was a huge deal. For over 2,000 years, people had assumed Euclid's parallel postulate had to be true. Remember, this postulate basically says that given a line and a point not on the line, there's exactly one line through the point parallel to the original line. It's more complicated than the other postulates, and mathematicians had always felt uneasy about it. Many tried to prove it from the other postulates, thinking it shouldn't need to be a separate assumption. They all failed. In the early 1800s, mathematicians like Nikolai Lobachevsky in Russia, János Bolyai in Hungary, and Gauss in Germany started wondering, what if you couldn't prove it because it's independent? What if you could have a consistent geometry where the parallel postulate is false? Lobachevsky published his work on hyperbolic geometry in 1829. In this geometry, through a point not on a line, there are infinitely many lines parallel to the given line. Angles and triangles sum to less than 180 degrees. The geometry is consistent, no contradictions arise. It's weird. Bolyai independently discovered similar results, publishing in 1832 as an appendix to his father's book. When Gauss saw Bolyai's work, he wrote back saying he'd discovered the same things years earlier but never published. This was devastating to Bolyai. You can also have elliptic geometry, where there are no parallel lines. On a sphere, for instance, all great circles intersect. There are no parallel lines. Angles in triangles sum to more than 180 degrees. Bernhard Riemann developed this systematically. This blew people's minds. It meant geometry wasn't just about describing physical space. It was an abstract, logical system. You could have different geometries depending on which axioms you chose. The parallel postulate isn't true or false in some absolute sense. It's just an assumption you can make or not make. This realization opened up mathematics to much more abstract thinking. Bernhard Riemann took this even further. His 1854 lecture on the hypotheses underlying geometry was revolutionary, though not fully appreciated at the time. Riemann proposed that space itself could have different geometries. He developed the concept of a manifold, a space that locally looks like Euclidean space but globally might have different properties. He introduced the Riemann curvature tensor, which measures how curved a space is. This was incredibly abstract and mathematical. Riemann wasn't thinking about physical space, he was just doing pure mathematics. But 50 years later, Einstein used Riemann's geometry as the framework for general relativity. Einstein's theory says that gravity is the curvature of space-time, and the mathematics that describes this curvature is Riemannian geometry. So Riemann's abstract mathematical ideas turned out to describe physical reality. Riemann also worked on complex analysis, the study of functions of complex variables. He gave rigorous definitions of integration for functions of complex variables, what we call Riemann integration. He studied what are called Riemann surfaces, ways to visualize multi-valued complex functions. Riemann introduced the Riemann zeta function, which he studied in relation to prime numbers. This function is zeta of s equals the sum of 1 over n to the s for all positive integers n, where s is a complex number. Riemann showed this function is deeply connected to the distribution of prime numbers. He proposed the Riemann hypothesis. All the non-trivial zeros of the zeta function have real part equal to 1/2. This remains unproven, one of the most important unsolved problems in mathematics. It has huge implications for number theory and the distribution of primes. Then we get to set theory. Georg Cantor, working in the late 1800s, developed a whole theory of sets and infinity. Cantor wanted to understand the nature of infinity mathematically. He started by asking, most people would say infinity is just infinity, there's only one. But Cantor showed you could compare the sizes of infinite sets. The set of even numbers and the set of all integers have the same cardinality because you compare each integer n with the even number 2n. This is weird because the evens are a proper subset of the integers. Cantor then asked, does the set of real numbers have the same cardinality as the integers? He proved it doesn't. Using his famous diagonal argument, he showed that any attempted listing of all real numbers will miss some. Therefore, the reals are a bigger infinity than the integers. He introduced transfinite numbers, different levels of infinity. The cardinality of the integers is called aleph 0. The cardinality of the reals is larger, called aleph 1 or C for continuum. Cantor asked whether there's any cardinality between aleph 0 and C. This is called the continuum hypothesis. He couldn't prove or disprove it, and it remains one of the most interesting questions in set theory. It was later shown that the continuum hypothesis is independent of the standard axioms of set theory, meaning you can't prove it or disprove it from those axioms. Cantor's work was controversial at the time. Some mathematicians, like Leopold Kronecker, strongly opposed it. Kronecker famously said, God made the integers, all else is the work of man, rejecting abstract constructions. He saw Cantor's transfinite numbers as nonsense. This opposition, plus personal struggles, contributed to Cantor suffering from depression later in life. But Cantor's set theory became the foundation for modern mathematics. David Hilbert defended it, saying, no one shall expel us from the paradise that Cantor has created. Today, set theory is how we build mathematics from the ground up. You start with sets, define numbers as certain types of sets, define functions as sets of ordered pairs, and build everything from there. Richard Dedekind was working on similar ideas around the same time. He used sets to construct the real numbers rigorously, using what are called Dedekind cuts. He developed clear notions of functions, not as formulas, but as correspondences between sets. He worked on abstract algebra, giving rigorous definitions of rings and fields. Speaking of abstract algebra, this field really took off in the 19th century. Évariste Galois is one of the most tragic figures in mathematics. He lived from 1811 to 1832, dying in a duel at age 20. The night before the duel, he frantically wrote down his mathematical ideas, knowing he might die. He did die, and his work was mostly ignored for years until it was finally published and understood. Galois developed what we now call Galois theory, which uses groups to study polynomial equations. He showed that you can associate a group, a set, with a multiplication operation to any polynomial equation. Properties of this group tell you about the solutions to the equation. Using this theory, Galois proved that there's no general formula for solving polynomial equations of degree 5 or higher, using just arithmetic and root extractions. The quadratic formula works for degree 2. There are formulas, though complicated, for degrees 3 and 4. But for degree 5 and up, no such formula exists. This answered a question mathematicians had been asking for centuries. Galois theory also explains which geometric constructions are possible with compass and straight edge. You can't trisect an arbitrary angle, or double the cube, or square the circle, problems the Greeks had tried. Galois theory explains why these are impossible. Group theory, which Galois helped found, became a major field. A group is a set with an operation that's associative, has an identity element, and where every element has an inverse. This simple structure appears everywhere. Symmetries form groups, permutations form groups, numbers under addition form a group. Group theory became crucial for studying symmetry in mathematics and physics. Arthur Cayley worked on group theory and matrices. He showed that every finite group is isomorphic to a group of permutations. William Rowan Hamilton invented quaternions in 1843. He was looking for a three-dimensional extension of complex numbers and realized he needed 4 dimensions. Quaternions have one real part and three imaginary parts. They're non-commutative, meaning ab doesn't always equal ba. This was the first time anyone had seriously worked with a non-commutative algebra. Quaternions are used today in computer graphics and spacecraft navigation because they handle three-dimensional rotations elegantly. Augustin Louis Cauchy, in the early 1800s, started making calculus more rigorous. Calculus had been used for over a century, but the foundations were still shaky. What exactly was a limit? What did it mean for a function to be continuous? Cauchy gave careful definitions. He defined limits in terms of making quantities arbitrarily small. A sequence converges to L if, for any small distance you choose, eventually all terms are within that distance of L. Karl Weierstrass took this even further in the mid-1800s, developing the epsilon delta definition of limits that we still teach today. To say the limit of f of x as x approaches a equals L means for any epsilon greater than 0, there exists a delta greater than 0, such that if the distance from x to a is less than delta and x is not equal to a, then the distance from f of x to L is less than epsilon. This is precise and rigorous. It removes the vague talk about infinitesimals and makes calculus logically solid. Weierstrass also found functions that were continuous everywhere but differentiable nowhere. Shocking examples showing that intuition about continuous functions could be wrong. He worked on complex analysis and power series. The Weierstrass M-test for uniform convergence of series is still used today. Around the same time, mathematicians were developing real analysis, making everything about real numbers and functions rigorous. They precisely defined what real numbers are, what continuity means, what convergence means. They proved theorems about when you can interchange limits, when series converge, when functions can be integrated. Moving into the 20th century now, there were huge questions about the foundations of mathematics. Mathematics had become very abstract. Set theory, non-Euclidean geometry, transfinite numbers, all sorts of weird and wonderful things. But what were the logical foundations? Could mathematics be put on a completely solid basis? In 1900, David Hilbert gave a famous lecture at the International Congress of Mathematicians in Paris. He posed 23 unsolved problems for the 20th century. These Hilbert problems guided research for decades. Some have been solved, some remain open, some turned out to be impossible to solve in their original form. Hilbert also promoted a program to formalize all of mathematics. He wanted to find a complete and consistent set of axioms from which all mathematical truths could be derived. He believed you could, in principle, reduce all of mathematics to mechanical symbol manipulation. He posed the Entscheidungs problem, the decision problem. Is there an algorithm to determine whether any given mathematical statement is true or false? Bertrand Russell and Alfred North Whitehead tried to ground all of mathematics in logic with their massive work Principia Mathematica, published in 3 volumes from 1910 to 1913. They wanted to show that math was just applied logic, that you could derive all of mathematics from logical axioms and rules of inference. The work is incredibly detailed and formal. It takes hundreds of pages to get to the point where they can prove that 1 plus 1 equals 2. Russell had earlier discovered a paradox in naive set theory. Consider the set of all sets that don't contain themselves. Does this set contain itself? If it does, then by definition it doesn't. If it doesn't, then by definition it does. Contradiction. This showed that you have to be careful about how you define sets. You can't just form sets in any way you want. Various ways to fix this were proposed. Zermelo-Fraenkel set theory with the axiom of choice, ZFC, became the standard. This is a system of axioms that avoids Russell's paradox and provides a foundation for mathematics. Almost all of modern mathematics can be formalized within ZFC. Then Kurt Gödel showed up and changed everything. Gödel lived from 1906 to 1978. In 1931, he published his incompleteness theorems, and they were bombshells. Gödel's first incompleteness theorem says that, in any consistent formal system powerful enough to express basic arithmetic, there are true statements that cannot be proved within that system. Let me say that again. If you have a set of axioms strong enough to do basic arithmetic, and if those axioms are consistent, meaning they don't lead to contradictions, Then there are true statements about numbers that your axioms can't prove. Gödel proved this by constructing a statement that essentially says this statement cannot be proved. If the statement is false, then it can be proved. But then the system proves false things and is inconsistent. If the statement is true, then it's a true statement that can't be proved, so the system is incomplete. Either way, the system is either inconsistent or incomplete. This shattered Hilbert's dream of a complete formal system for all mathematics. No matter what axioms you start with, as long as they're consistent and strong enough to do arithmetic, there will always be true statements you can't prove from those axioms. Mathematics is inherently incomplete. Gödel's second incompleteness theorem says that no consistent system can prove its own consistency. If a system is strong enough to do basic arithmetic, it can't prove that it won't lead to contradictions. You can prove consistency from a stronger system, but then you need to trust that stronger system, and it can't prove its own consistency either. It's turtles all the way down. These results showed there are inherent limits to what we can prove. They don't mean mathematics is broken or unreliable. Mathematical proofs still work. But they mean there's no ultimate foundation, no final set of axioms that settles everything. Then, in 1936, Alan Turing and Alonzo Church independently showed that Hilbert's Entscheidungs problem was unsolvable. The decision problem is undecidable. Turing invented an abstract computational device, the Turing machine, to prove this. A Turing machine has an infinite tape divided into cells, a read-write head that can move along the tape, and a set of states and rules. Despite being simple, a Turing machine can perform any computation that any computer can. Turing showed that the halting problem is undecidable. You can't write a program that takes another program as input and always correctly determines whether that program will halt or run forever. If you could solve the halting problem, you could solve the decision problem, but Turing proved the halting problem is unsolvable. In doing this, Turing basically founded computer science. The Turing machine became the theoretical foundation for all modern computers. Any algorithm that can be computed by any computer can be computed by a Turing machine. This is the Church-Turing thesis, named after Turing and Alonzo Church, who developed lambda calculus. Church and Turing independently proved the undecidability of the decision problem using their different models. They then showed these models were equivalent in computational power. The Church-Turing thesis says that any effectively calculable function can be computed by a Turing machine. This isn't a theorem you can prove. It's a thesis about what computable means, but it's widely accepted. Turing later worked on artificial intelligence, asking whether machines can think. He proposed the Turing test. A machine can be considered intelligent if a human can't reliably distinguish its responses from a human's in a conversation. During World War II, Turing worked at Bletchley Park on breaking the German Enigma code, making crucial contributions to the Allied victory. After the war, he worked on early computers and theoretical biology. Tragically, he was prosecuted for homosexuality in 1952 and died in 1954, likely by suicide, though some think it was an accident. Let's talk about the middle and later 20th century now. Mathematics exploded in scope and sophistication. Hundreds of specialized subfields developed. We can't cover everything, but let's hit some highlights. Category theory emerged as a way to unify different mathematical structures. Instead of focusing on the objects themselves, category theory focuses on the relationships between objects, the morphisms. Samuel Eilenberg and Saunders MacLean developed category theory in the 1940s. It's incredibly abstract, dealing with concepts like functors, natural transformations, and adjunctions. Some people joke it's abstract nonsense, but it's turned out to be powerful for seeing connections between different areas of math. Topology became a major field. Topology studies properties of spaces that don't change under continuous deformations. A coffee cup and a donut are topologically the same, because you can continuously deform one into the other without tearing or gluing. But a donut and a sphere are topologically different because a sphere has no holes. Henri Poincaré, in the late 19th and early 20th centuries, was a pioneer in topology. He studied what we call algebraic topology, using algebraic tools like groups to study topological spaces. In 1904, Poincaré posed a question that became the Poincaré conjecture. Is every simply connected, closed three-dimensional manifold homeomorphic to a three-dimensional sphere? In simpler terms, if a three-dimensional space has a certain nice property, no holes, is it basically just a three-dimensional sphere? This remained unsolved for over a century. It was one of the Clay Mathematics Institute's Millennium Prize problems, each worth $1 million. In 2003, Grigory Perelman, a Russian mathematician, posted a proof online. He used techniques from differential geometry and geometric analysis, studying the Ricci flow on manifolds. His proof was checked and verified over several years. He was awarded the Fields Medal in 2006 and the Millennium Prize in 2010. But here's the thing. Perelman declined both awards. He refused the Fields Medal at the ceremony. He declined the $1 million prize. He'd become disillusioned with mathematics as a social enterprise, didn't like the competition and politics. He largely withdrew from the mathematical community. His refusal of the prizes was shocking and made headlines. But his proof stands as one of the great achievements of recent mathematics. Chaos theory and fractals developed in the late 20th century and showed how simple rules could produce incredibly complex behavior. Edward Lorenz, a meteorologist, was running weather simulations on a computer in the early 1960s. He noticed that tiny differences in initial conditions led to wildly different outcomes. He was investigating whether you could predict weather long-term, and he realized you couldn't because weather is chaotic. Small uncertainties get amplified exponentially. This became known as the butterfly effect. A butterfly flapping its wings in Brazil could theoretically cause a tornado in Texas weeks later through the cascading effects of atmospheric dynamics. Lorenz discovered what's now called the Lorenz attractor, a strange attractor in a three-dimensional system. When you plot the solutions to his weather equations, they trace out this beautiful butterfly-shaped figure looping around in a complex but organized way. The system is deterministic. The equations tell you exactly how it evolves, but it's unpredictable because tiny changes grow exponentially. Chaos theory showed that deterministic systems can be unpredictable. This was philosophically significant. Laplace had imagined a deterministic universe where everything could be calculated if you knew the initial conditions precisely enough. But chaos theory shows that even simple deterministic systems can be effectively random because you can never measure initial conditions with infinite precision. Benoit Mandelbrot pioneered fractal geometry in the 1970s and 80s. Fractals are shapes that have self-similarity at different scales. Zoom in on a fractal and you see similar patterns. Mandelbrot showed that many natural phenomena, like coastlines, clouds, mountains, and blood vessels, have fractal properties. He coined the term fractal and studied their mathematics. The Mandelbrot set is a fractal defined by a simple rule involving complex numbers. For each complex number c, you repeatedly apply the function f of z equals z squared plus c, starting with z equals 0. If the sequence stays bounded, c is in the Mandelbrot set. If it goes to infinity, it's not. When you plot this, you get this incredibly intricate shape with infinite detail. You can zoom in forever and keep finding new structures. The boundary of the Mandelbrot set has a fractal dimension, not an integer dimension like a curve or surface, but something in between. Fractals became popular partly because computers could generate beautiful images of them. The Mandelbrot set with its swirling tendrils and recursive detail became an icon. But fractals are also mathematically deep and practically useful for modeling natural phenomena that have self-similarity and rough, irregular structure. Number theory saw major advances in the 20th century. Andrew Wiles proved Fermat's last theorem in 1994 after working on it in secret for 7 years. Remember, Fermat claimed that a to the n plus b to the n equals c to the n has no positive integer solutions for n greater than 2, and he wrote that he had a proof, but the margin was too small. For over 350 years, mathematicians tried to prove this. Special cases were proved for specific values of n, but the general case remained open. Wiles, inspired since childhood by this problem, worked on it using incredibly advanced techniques. He connected the problem to elliptic curves and modular forms, two areas of modern mathematics. He proved enough about elliptic curves to show that Fermat's last theorem had to be true. His proof was hundreds of pages long and used cutting-edge algebraic geometry. He announced it in 1993, but then a gap was found in the proof. Wiles spent another year fixing it with help from Richard Taylor. The final proof was published in 1995. It's considered one of the great achievements of 20th century mathematics. Wiles received numerous prizes, though he couldn't get the Fields Medal because he was over 40. The age limit for that prize. He did receive the Abel Prize in 2016. Computers became a tool for mathematical research. They could verify calculations, search for patterns, test conjectures, and even help with proofs. The four-color theorem, which says any map can be colored with at most 4 colors so that no adjacent regions have the same color, was proved in 1976 by Kenneth Appel and Wolfgang Haken. They reduced the problem to checking many cases, and a computer verified them all. This was controversial at first. Can a proof rely on computer calculations that no human can check by hand? But it's now accepted, and computer-assisted proofs have become more common. Graph theory became a major field, partly driven by practical applications in computer science and operations research. Graphs are collections of vertices connected by edges. You can model all sorts of things as graphs: social networks, transportation networks, chemical molecules, computer networks. Graph theory studies properties like connectivity, paths, cycles, colorings, and matchings. Game theory, developed by John von Neumann and Oscar Morgenstern in the 1940s, applies mathematics to strategic decision-making. Game theory analyzes situations where multiple agents make decisions that affect each other. It's used in economics, political science, biology, and many other fields. John Nash, made famous by the movie A Beautiful Mind, proved the existence of Nash equilibria, strategy profiles, where no player wants to change their strategy given what others are doing. Optimization theory studies how to find the best solution to problems with constraints. Linear programming, developed during World War II for logistics, finds optimal solutions when the objective and constraints are linear. The simplex algorithm by George Dantzig solves linear programming problems efficiently in practice, though worst case it can be slow. Interior point methods developed later provide polynomial time algorithms. Cryptography became mathematically sophisticated in the late 20th century. Public key cryptography, invented by Whitfield Diffie, Martin Hellman, and Ralph Merkle, and independently by Ron Rivest, Adi Shamir, and Leonard Edelman with the RSA algorithm, relies on number theory. RSA encryption uses the fact that multiplying large primes is easy, but factoring the product is hard. Elliptic curve cryptography uses the mathematics of elliptic curves. Modern internet security relies on these mathematical ideas. Coding theory developed to handle errors in data transmission. Richard Hamming invented error-correcting codes in the 1950s. Claude Shannon's information theory provided mathematical foundations for understanding information, entropy, and channel capacity. Reed-Solomon codes, invented in 1960, are used in CDs, DVDs, and QR codes. Combinatorics, the study of counting in discrete structures, expanded greatly. How many ways can you arrange objects? How many structures of a certain type exist? These questions come up in computer science, probability, and many areas. Ramsey theory studies conditions under which order must appear. The pigeonhole principle says, if you have more pigeons than pigeonholes, some pigeonhole must have at least 2 pigeons. Simple, but surprisingly powerful. Computability theory and computational complexity theory. Of those that are computable, some are much harder than others. The P versus no problem asks whether problems whose solutions can be quickly verified can also be quickly solved. This is one of the Millennium Prize problems, still unsolved. It's one of the most important open questions in computer science, with huge implications for mathematics, cryptography, and many fields. Mathematical logic became a deep field studying formal systems, proof theory, model theory, and set theory. Logicians studied different axiomatic systems, investigated what can be proved, and explored the boundaries of consistency and decidability. Paul Cohen proved the independence of the continuum hypothesis from ZFC set theory in 1963 using forcing, a technique that constructs models of set theory with desired properties. This means the continuum hypothesis can neither be proved nor disproved from the standard axioms. You can consistently add it or its negation as an additional axiom. Algebraic geometry became incredibly sophisticated. It studies solutions to systems of polynomial equations using geometric and algebraic techniques. In the 20th century, algebraic geometry was revolutionized by Alexander Grothendieck and others. Grothendieck introduced schemes, a vast generalization of varieties, and developed new cohomology theories. His work is notoriously abstract and difficult, but enormously influential. The wild conjectures about counting solutions to polynomial equations over finite fields were proved using these techniques. Representation theory studies how abstract algebraic objects can be represented by matrices and linear transformations. It connects algebra, geometry, and analysis. Representations of groups are used in physics to study symmetries of particles and crystals. Differential equations remain central to applied mathematics. Partial differential equations describe wave propagation, heat flow, fluid dynamics, quantum mechanics, and much more. Numerical methods for approximately solving PDEs on computers are crucial for engineering and science. Finite element methods, finite difference methods, and spectral methods are techniques for discretizing and solving PDEs computationally. Probability theory and statistics advanced enormously. Kolmogorov gave probability a rigorous foundation using measure theory in the 1930s. Stochastic processes, random processes, evolving over time, became a major area. Brownian motion, Markov chains, and Poisson processes model all sorts of random phenomena. Statistics developed sophisticated methods for inference, hypothesis testing, regression, and data analysis. Bayesian statistics interprets probability as degree of belief and updates beliefs based on evidence. The 20th century also saw mathematics become more collaborative and international. Mathematicians from all over the world contributed. The Fields Medal, established in 1936 and first awarded in 1936, became the most prestigious prize in mathematics, awarded every 4 years to mathematicians under 40. The Abel Prize, established in 2003, honors lifetime achievements without age restriction. Women gradually gained more recognition in mathematics, though they still faced barriers. Emmy Noether, working in the early 20th century, made groundbreaking contributions to abstract algebra and theoretical physics. Noether's theorem connects symmetries to conservation laws and is fundamental in modern physics. She worked in a time when women couldn't officially hold academic positions, but her influence was immense. Other women, like Sofia Kovalevskaya, Olga Ladizanskaya, Karen Uhlenbeck, and Maryam Mirzakhani, made major contributions. Mirzakhani was the first woman to win the Fields Medal in 2014 for her work on the geometry of Riemann surfaces and dynamical systems. She tragically died of cancer in 2017 at age 40. So, here we are today. Mathematics is more active than ever. Researchers are working on problems across hundreds of specialized subfields. We have the Clay Millennium Prize problems, 7 major unsolved problems, each worth $1 million. Only one, the Poincaré conjecture, has been solved so far. The Riemann hypothesis about the zeros of the Riemann zeta function remains unsolved. It's been verified for trillions of zeros numerically, but no proof exists. If proved, it would have huge implications for number theory and the distribution of primes. The P versus no problem problem asks whether problems whose solutions can be quickly verified can also be quickly solved. Quickly here means polynomial time. If P equals no problem, it would revolutionize computer science. Cryptography would break. Many hard optimization problems would become easy. Most computer scientists believe P doesn't equal no problem, but proving it has been elusive. The Hodge conjecture concerns algebraic cycles on complex algebraic varieties. It's about whether certain cohomology classes come from algebraic subvarieties, very abstract and technical. The Birch and Swinnerton-Dyer conjecture. relates the number of rational points on elliptic curves to properties of an associated L function. It's a deep connection between geometry and analysis. The Navier-Stokes existence and smoothness problem asks whether solutions to the Navier-Stokes equations, which describe fluid flow, always exist and are smooth. These equations are used constantly in engineering, but we don't have a complete mathematical theory of their solutions. The Yang-Mills existence and mass gap problem concerns quantum field theory and asks whether Yang-Mills theories have a mass gap and whether a rigorous mathematical framework can be established. This bridges mathematics and theoretical physics. Mathematicians are exploring higher dimensional topology, studying manifolds in 4, 5, and higher dimensions. 4-dimensional topology is particularly tricky. You might think it gets harder as dimension increases, but actually dimension 4 is in some ways the hardest. Dimension 3 has Perelman's work. Dimensions 5 and higher have techniques that work well. Dimension 4 is special and difficult. Algebraic geometry continues to be a deep and active field. Mathematicians study moduli spaces, parameter spaces of geometric objects. They use techniques from category theory, homological algebra, and derived categories. The Langlands program, initiated by Robert Langlands in the 1960s, proposes deep connections between number theory and representation theory. It's a vast web of conjectures, some proved, many open, unifying different areas of mathematics. Mathematicians are using computers more than ever, both for computation and proof verification. Computer algebra systems can perform symbolic calculations. Proof assistants like Coq, Lean, and Isabelle let you write formal proofs that the computer verifies for correctness. Some mathematicians are working on formalizing large parts of mathematics to make sure there are no errors. Machine learning and AI are being used to discover new mathematical patterns and conjectures. Systems have found new connections between mathematical objects, suggested conjectures, and even helped with parts of proofs. DeepMind's AlphaGo and AlphaZero, which mastered Go and chess, showed that AI can develop intuition in complex domains. Researchers are exploring whether similar techniques can help with mathematical research. Applied mathematics has never been more important. Math drives modern technology in countless ways. Cryptography keeps internet communication secure. Error-correcting codes ensure data integrity. Algorithms power search engines, recommendation systems, and social media. Mathematical models help us understand climate, weather, epidemics, and economies. Simulations using finite element methods and computational fluid dynamics are essential for engineering everything from airplanes to smartphones. Data science and machine learning rely heavily on mathematics. Linear algebra for manipulating data matrices, calculus for optimization, algorithms like gradient descent, probability and statistics for inference and uncertainty quantification. Neural networks are mathematical functions with millions of parameters trained using calculus-based optimization on huge data sets. Mathematical biology uses differential equations to model population dynamics. Mathematical ecology studies predator-prey systems and ecosystem stability. Bioinformatics applies algorithms and statistics to analyze genetic data. Mathematical finance uses stochastic calculus to model stock prices and derivatives. The Black-Scholes equation for option pricing, derived in the 1970s by Fisher Black, Myron Scholes, and Robert Merton, won a Nobel Prize in economics. It uses ideas from heat diffusion equations in physics to price financial options. Pure mathematics continues to surprise us with unexpected connections between seemingly unrelated areas. A theorem in number theory might suddenly prove useful in cryptography or error correction. A topological idea might solve a problem in data analysis. The modularity theorem, which Wiles proved as part of proving Fermat's last theorem, connects elliptic curves and modular forms, two areas that seemed unrelated. Mathematics is also becoming more aware of its history and its connections to other cultures. We're learning more about mathematics in ancient and medieval civilizations beyond the traditional Western narrative. Chinese, Indian, Islamic, and African mathematical traditions had their own developments that contributed to the global mathematical heritage. Mathematics is increasingly collaborative. Large projects involve dozens or hundreds of researchers. The classification of finite simple groups Completed in the 1980s and revised since, was a massive collaborative effort producing tens of thousands of pages of proofs. The polymath projects, started by Timothy Gowers, use blogs and wikis for massive online collaboration on specific problems, with many mathematicians contributing ideas. Mathematics is also grappling with questions about the nature of mathematical reality. Are mathematical objects real, existing independently of humans, and we discover them? Or are they human constructions, and we invent them? This philosophical question, realism versus anti-realism, has been debated for millennia and remains unresolved. There's also discussion about the role of intuition versus formal rigor. Human mathematicians use intuition, visualization, and informal reasoning to discover things, then they formalize it into rigorous proofs. Can computers develop mathematical intuition? Can AI generate new mathematics? These are open questions. The accessibility of mathematics is improving. Online resources, lecture videos, and interactive software make learning mathematics easier than ever. But math education remains challenging, and many people struggle with it. There's ongoing debate about how to teach mathematics effectively, whether to emphasize memorization or understanding, computation or concepts. Looking back at this entire journey, what's amazing is how universal mathematics is. Completely separate civilizations developed similar ideas independently. The Babylonians, Greeks, Chinese, Indians, and Mayans all came up with sophisticated mathematical systems. Basic mathematical truths like the Pythagorean theorem or properties of prime numbers were discovered multiple times in different places. Once different mathematical traditions met and merged, particularly during the Islamic Golden Age and the European Renaissance, progress accelerated. Ideas flowed between cultures. Indian numerals reached Europe through the Islamic world. European calculus spread to China and Japan. Mathematics became a global endeavor. Mathematics is cumulative in a way few other fields are. Once a theorem is proved, it stays proved. Euclid's geometry is as valid today as it was 2,300 years ago. Newton and Leibniz's calculus is still taught and used. Gauss's number theory remains relevant. Each generation builds on what came before. But mathematics is also creative. It's not just about following rules or applying known techniques. It's about asking new questions, seeing new patterns, making unexpected connections. It's about taking abstract ideas and pushing them to see where they lead. Cantor's transfinite numbers, Gödel's incompleteness theorems, Turing's abstract computers, all of these were creative leaps that changed how we think. Mathematics has both beauty and utility. Some mathematics is done for its own sake, for its elegance and structure, with no practical application in mind. Pure mathematics pursues questions because they're interesting, not because they're useful. Number theory, once the quintessence of pure math, now secures internet transactions. Non-Euclidean geometry, a curiosity, became the language of general relativity. Abstract algebra underpins cryptography and error correction. Mathematics is also a human endeavor. Behind every theorem is a person or group of people who struggled with ideas, made mistakes, had insights, and worked hard to understand. The history of mathematics is full of brilliant minds, but also rivalry, controversy, tragedy, and triumph. Tartaglia and Cardano fighting over credit. Newton and Leibniz's bitter dispute. Galois dying young in a duel. These human stories remind us that mathematics, for all its abstraction, is created by real people. Most importantly, mathematics is ongoing. We haven't figured everything out, not even close. There are still mysteries, still unsolved problems, still new areas to explore. Every answer raises new questions. Some of the biggest questions in mathematics remain unanswered. The Riemann hypothesis standing for over 160 years. The P versus no problem, with implications for all of computation. The Birch and Swinnerton-Dyer conjecture about elliptic curves. Whether the Navier-Stokes equations always have smooth solutions. These problems are hard, really hard, but that's what makes them interesting. New areas of mathematics continue to emerge. Topological data analysis uses topology, to find structure in high-dimensional data. Quantum computing requires new mathematics to understand quantum algorithms and error correction. Mathematical biology is growing as we apply mathematics to understanding life at the molecular and cellular level. Mathematics is also becoming more interdisciplinary. The boundaries between pure and applied math are blurring. Mathematicians work with physicists on string theory and quantum field theory. They work with computer scientists on algorithms and complexity. They work with biologists on modeling evolution and ecosystems. They work with economists on game theory and market behavior. Mathematics touches everything. The tools of mathematics are changing too. Computers enable calculations and visualizations impossible by hand. The internet lets mathematicians collaborate globally in real time. Open access publishing and preprint servers like argziv make research available immediately. Proof assistants may change how we verify mathematics. Artificial intelligence might help discover new patterns and conjectures. But at its core, mathematics is still about the same thing it's always been about: understanding patterns, structures, and relationships, asking why things are the way they are, proving that something must be true, finding connections between different ideas, taking a problem and figuring out how to solve it. The tools change, the areas grow, but the fundamental activity remains. Who knows what mathematical breakthroughs the 21st century will bring? Maybe someone will prove the Riemann hypothesis, unlocking deep secrets about prime numbers. Maybe someone will solve P versus no problem, revolutionizing computer science. Maybe someone will discover new mathematical structures we can't even imagine yet. Maybe quantum computers will change what's computably tractable. Maybe AI will become a collaborator in mathematical research, not just a tool, but a partner in discovery. One thing seems certain: mathematics will continue to surprise us. It will continue to reveal beautiful structures and unexpected connections. It will continue to be useful in ways we can't predict. And it will continue to be one of humanity's greatest intellectual achievements. That's the story of math. From ancient bone counters to modern quantum computers. From Egyptian surveyors to category theorists. From the Pythagorean theorem to the classification of finite, simple groups. It's been a long, weird, brilliant journey spanning cultures and millennia. It's a story of human curiosity, creativity, and determination to understand the abstract structures underlying reality. And it's far from over. Mathematics is alive and thriving. Every day, mathematicians around the world are working on problems, proving theorems, discovering new connections, and pushing the boundaries of human knowledge. The next chapter of the story is being written right now. Maybe you'll be part of it.